The ground beneath our feet holds a secret written in perfectly straight lines. Scattered across deserts, valleys, and remote plateaus on nearly every continent, you can find precise parallel grooves cut deep into solid bedrock. They look like the work of a machine, yet they appear in places separated by thousands of miles and wildly different climates. This video will give you a front-row seat to a genuine scientific detective story, one that could force us to rewrite chapters of our planet's history. Why do identical markings appear from Death Valley to Saudi Arabia? Could the accepted story of slow, grinding glaciers be wrong? We will explore the startling possibilities, from continent-scouring mega-tsunamis to forces even more extraordinary. By the end, you will understand why this stone-carved mystery challenges everything we think we know about Earth's past. What does it mean if our world's calm surface hides evidence of a global cataclysm? These grooves are a geological fingerprint, a signature left by something immense. To understand the mystery, we must first look closely at the mark itself. Picture, if you will, a vast sheet of ancient granite or limestone smoothed by time. Upon this surface, you do not see the chaotic web of natural fractures. Instead, you see lines, dozens, sometimes hundreds of them, running side by side like tracks laid down by a phantom train. Each groove is a shallow trench, perhaps an inch or two deep, carved with a surgeon's precision into stone that would blunt modern steel tools. The spacing between them is often eerily consistent, and their direction holds unwavering across miles of terrain. This is not the work of a trickling stream or a sporadic rock slide. This is the evidence of a force that moved across the landscape with singular purpose and unimaginable power, scouring the very bones of the continent as it passed. That force, for over a century, has had a name in geology textbooks. It is called a glacier. These same precise, parallel grooves etched into the bedrock. This is the core of the desert dilemma. These regions have been intensely arid, some for tens of millions of years. The climate models and the geological record here tell a story of relentless sun and wind, not of creeping ice and snowfall. To propose that continental-scale glaciers, miles thick, once blanketed these latitudes requires a complete reimagining of Earth's climatic past, one for which we currently lack supporting evidence. The very ground itself seems to argue against it. Where are the massive piles of glacial till, the sculpted valleys, the other undeniable fingerprints a retreating ice sheet would leave behind? They are largely absent. So we are left with a haunting question. If the ice never came here, what powerful hand drew the same straight lines upon the stone? The desert's silent stones force us to consider a far more violent artist. If not ice, then perhaps water, but not the gentle kind. One compelling alternative now gaining serious attention is the mega-tsunami hypothesis. Imagine for a moment not a slow grinding glacier, but a single planet-altering event. Proponents of this idea suggest these parallel grooves were carved in hours, not by catastrophic waves of unimaginable scale. The trigger could have been a colossal asteroid impact in an ocean basin or a massive submarine landslide. Such an event would displace cubic miles of seawater, sending a wall of water hundreds, even thousands of feet high, racing across continents at jetliner speeds. This is not a wave that merely floods a coast. This is a wave that reshapes geography. As this mountain of water charges inland, it does not travel cleanly. It transforms into a dense, churning slurry, a thick soup of seawater, mud, and every piece of rock and debris it scours from the landscape. This abrasive mixture, moving with terrifying unity and direction, would act like a sheet of liquid sandpaper dragged across the continent's face. The consistent, parallel grooves we find could be the signature of this singular, devastating pass. The force would be so immense, so focused, that it could carve straight lines into solid granite as easily as a river cuts through soft soil. This hypothesis elegantly solves several puzzles. It explains why we find identical markings in now arid deserts that were once closer to ancient coastlines. It accounts for grooves found at surprisingly high elevations, on plateaus we once thought were safe from any flood. Most compellingly, it offers a single, unifying explanation for a global phenomenon. Instead of unrelated glaciers in impossible places, we see the scars from one or several planet-wide cataclysms. The stones, in this light, are not a record of a slow climate. They are a monument to a single, terrible day in Earth's history. But could water truly be that powerful? And is there any proof such an event ever occurred? The channeled Scablands of Washington state offer a terrifying glimpse of what water is truly capable of. This landscape looks like it belongs on another world, a vast terrain of dry waterfalls, colossal potholes, and canyons with no river in sight. Its story is one of the most dramatic discoveries in modern geology. For decades, scientists believed these features were carved slowly by glaciers or rivers. Then, a geologist named Jay proposed something radical. He argued the Scablands were not sculpted by patience, but by a single, unimaginable flood. His idea was mocked for years, seen as a return to outdated notions of biblical deluges. But the evidence was simply too overwhelming to ignore. We now know that near the end of the last ice age, a colossal ice dam holding back a vast inland sea, glacial Lake Missoula, catastrophically failed. The result was not a flood, it was a wall of water. Imagine a torrent equal to 10 times the combined flow of every river on Earth today, unleashed in a matter of days. This liquid bulldozer ripped across hundreds of miles of solid basalt plateau, carving channels hundreds of feet deep and leaving behind those haunting, streamlined rock formations. The Scablands are a testament to the fact that water, given enough volume and speed, can perform geological surgery. It does not just erode, it sculpts with brutal, directed force. Now take that concept and scale it up by an order of magnitude. If the collapse of an ice dam in Montana could reshape an entire region, what could a wave generated by a miles-wide asteroid impact accomplish? The energy involved would be planetary. A mega tsunami of that scale would not merely flood coastlines, it would become a continent scouring event. The churning, debris-laden slurry at its leading edge would possess the consistency and abrasive power of flowing concrete. As it raged inland, it would not carve random patterns. It would flow in coherent, directional sheets, potentially explaining the precise, parallel nature of the grooves found worldwide. The Scablands provide our closest real-world analogy, a scale model written in stone that screams one undeniable truth. The calm geology we often take for granted can, in an instant, be by a force of almost incomprehensible violence. Yet the mega tsunami theory, for all its compelling power, is not the only radical idea on the table. There exists a far more controversial explanation, one that steps entirely outside the conventional box of ice and water. A small group of researchers proposes that these parallel grooves are not the result of any earthly force we currently understand. They suggest the marks are electrical scars. This is the core of the plasma discharge or electric universe hypothesis. In this view, the grooves are not carved by grinding or flooding, but etched by lightning on a scale that defies belief. Imagine a cosmic electrical arc, a bolt of plasma stretching from the heavens to the ground, but 1,000s of miles long and unimaginably more powerful than any storm we see today. Proponents argue that such an event, perhaps caused by a close encounter with a charged celestial body or within a vastly different ancient atmosphere, could have swept across the landscape. The searing, directed energy would not just scrape the rock, it would fuse it, leaving behind what are known as figures, the branching, fractal patterns electricity etches into surfaces. The advocates for this idea point to specific features they say mechanical theories cannot easily explain. They note rare instances where the grooves seem to branch or fork in patterns reminiscent of electrical discharge. They point to tiny pockets of melted glass, called fulgurites, sometimes found in association with the grooves, which are the known fingerprints of extreme electrical heat. They also highlight magnetic anomalies in the rock, suggesting the stone itself was fundamentally altered in an instant. To them, the precise parallelism and the sheer scale point not to a flowing substance, but to a standing wave of energy that momentarily connected the sky to the ground, machining the bedrock like a natural stencil. Mainstream geology largely views this hypothesis with deep skepticism, citing a lack of reproducible evidence and mechanisms that contradict established physics. Yet its value may not lie in being proven right, but in the profound question it forces us to confront. For centuries, we have explained our planet's shape through slow, mechanical forces, gravity, and erosion. This electrical scouring theory dares to ask, what if Earth's history also includes chapters written in sudden, catastrophic bursts of energy from the cosmos itself? It challenges the very framework of our geological storytelling, pushing us to wonder if we have been reading only half the sentences in the stone's autobiography. These theories all leave their own unique signature in the stone. To choose between them, we must become forensic detectives, examining the grooves themselves with a scientist's eye. The first clue is their remarkable uniformity. Unlike a river's erratic path or a rockslide's chaotic scarring, these lines maintain a consistent depth and width, sometimes for miles on end. They run parallel with a precision that suggests a single, unified force, not a collection of random events. The surface inside the groove often holds another telling detail. It can possess a smooth, almost polished appearance, sometimes covered in a dark, shiny coating known as desert varnish, a natural patina that forms over immense periods. But the most critical evidence lies deeper, in the very molecular structure of the rock. In some locations, the bedrock within the groove shows signs of having been transformed in an instant. The stone was heated so intensely, so rapidly, that it momentarily and then forming a thin, glassy skin. To a geologist, this layer is a mineralogical fingerprint. The traditional glacial theory calls this a friction melt, suggesting the incredible heat generated by rocks grinding under immense pressure. The electrical hypothesis points to the same feature and gives it a different name: fulgurite, the glassy tube left behind by a lightning strike. Here lies the core of the modern debate. Both catastrophic water and catastrophic electricity could, in theory, generate enough energy to melt rock. The question becomes, which process leaves a pattern in the glass that matches the pattern on the landscape? Analyzing this microscopic layer, its bubbles, its crystal structure, its magnetic properties, is like dusting for fingerprints at a cosmic crime scene. The answer encoded there could tell us whether the sculptor was a wave of unimaginable force or a bolt of energy from the heavens. These grooves form a compass pointing to the past. Their direction is not a random scribble, but a deliberate arrow, a record of the immense force that created them. In any given region, whether the American Southwest or the Arabian Peninsula, the vast majority of these parallel lines will align in one predominant orientation. To a geologist, this is a paleocurrent indicator, a fancy term for an ancient flow direction. It tells you which way the sculptor was moving when it etched its signature into the stone. If the grooves were made by a glacier, the lines show the glacier's path. If they were carved by a mega tsunami, they reveal the inland rush of that catastrophic wave. The direction is the first vital clue in retracing the steps of a planetary event. But the real mystery deepens when we zoom out from a single site to look at the entire globe. Imagine plotting every known set of these grooves on a world map, each with its own little arrow showing its local flow direction. What pattern would emerge? Would the arrows in North America all point north, suggesting a retreating ice sheet? Or would they radiate outward from a central point, like spokes on a wheel, hinting at an epicenter of unimaginable force? Would the patterns in Africa and Arabia converge, indicating a shared source from an ancient sea, or would they diverge in a chaotic spray? This global directional data is a cryptic map of past planetary dynamics, a puzzle waiting to be assembled. Decoding it could, in theory, point us toward ground zero. It could reveal whether we are looking at the aftermath of multiple unrelated events, or the singular scar of one global cataclysm. The lines in the stone are not just markings, they are a frozen moment of motion, a snapshot of a force in transit. By reading their alignment, we are attempting to reconstruct the last known address of a planet-shattering event, following a trail of stone breadcrumbs back to the moment everything changed. The sculptor left its tools behind. To carve straight lines into granite, you need something harder than granite itself. So the question becomes a simple one of mechanics. What was the cutting tool? Every theory of the grooves requires an abrasive, a hard substance dragged across the stone to grind it down. But the nature of that abrasive changes dramatically depending on the artist you imagine. In the classic glacial story, the abrasive is straightforward. It is the rocks themselves, everything from fine sand to car-sized boulders, plucked from the mountainside and frozen into the moving ice. This creates a natural grinding paste, a giant sheet of sandpaper a mile thick, inching forward for centuries. The evidence should be scattered all around the grooves, a trail of crushed rock and distinctive glacial till. For the mega tsunami, the abrasive is more chaotic but equally potent. The leading edge of that catastrophic wave is not clear water. It is a churning, viscous slurry, a thick soup of seawater, mud, sand, gravel, and every piece of debris scoured from the ocean floor and the coastline it overruns. This dense mixture acts like a fluid sander, with the suspended sediment doing the cutting as the entire mass rages inland. You would expect to find layers of unusual sediment deposits, perhaps far inland, that match this story. The most radical theory, the electrical discharge, proposes a different kind of abrasive altogether. Here, the cutting tool is not physical grit, but energy itself. The intense heat and kinetic force of the plasma arc could theoretically vaporize or fuse the surface of the rock without needing any added sediment. The abrasive, in this case, is the molecular disruption caused by unimaginable voltage. This would leave a very different signature, perhaps with little to no foreign debris in the groove itself, but with the rock's own chemistry transformed. So the detective work moves to a microscopic level. Inside those glassy linings sometimes found in the grooves, scientists search for tiny, trapped prisoners of the past. Are there minuscule fragments of quartz or basalt that could only have been transported from hundreds of miles away, hinting at a massive flow? Or is the glass pure, fused from the local bedrock alone, suggesting an intense, localized heat? Each tiny grain tells a story. Finding a consistent layer of fine, well-sorted sand embedded in the glaze would powerfully support the tsunami model. Discovering a mix of large, angular rock fragments might point back to glacial grinding. And finding almost no foreign material at all, just the remelted skin of the original stone, would force us to take the electrical idea much more seriously. The truth of what passed over these stones may be written in a language of minerals we are only just learning to read, but a geological mystery cannot be solved without a clock. The grooves are there, but the question of when they were carved is a puzzle wrapped in stone. Dating these enigmatic lines is one of the most difficult challenges facing researchers, because the bedrock itself is ancient, formed millions or even billions of years ago. The grooves are merely a recent modification, a scratch on the surface of deep time. How do you date a scratch? You cannot use carbon dating on solid granite. Instead, scientists have to become detectives of time, using indirect and ingenious methods to bracket the moment of creation. One approach is to look for something that covers the groove, like a layer of volcanic ash or a sediment deposit. If you can date that covering material, you know the groove must be older. Another cutting-edge technique involves measuring cosmic fingerprints. When bedrock is first exposed to the sky, it begins to be bombarded by cosmic rays from space. These rays transform atoms within the stone into rare isotopes called cosmogenic nuclides. By carefully measuring the buildup of these isotopes in the surface of the groove, scientists can calculate how long that surface has been exposed to the open air. It is like reading a very slow, very subtle radiation clock that started ticking the moment the carving was finished. The results from these methods, however, have not provided a neat answer. They have instead opened a wider mystery. Current estimates for these grooves span an enormous range. Some sites, particularly in North America, suggest dates within the last ice age, the Pleistocene epoch, perhaps tens or hundreds of thousands of years old. This would align them with known periods of dramatic climate change. Yet other sites, especially in arid regions far from recent glaciers, yield dates that are far more ancient, pushing back into epochs long before humans walked the Earth. This disparity is the core of the timeline problem. Do these wildly different dates mean we are looking at different phenomena altogether, unrelated events separated by millions of years? Or could they be revealing the limits of our dating techniques when applied to such an unusual feature? The answer to this question of when is the key that unlocks the what. If researchers can one day demonstrate, with high confidence, that grooves from the Saudi desert, the American Southwest, and the African plateau all formed at precisely the same moment in deep time, the case for a single global cataclysm becomes overwhelming. It would be the geological equivalent of finding the same unique fingerprint at crime scenes across the world. Conversely, if the dates remain stubbornly different, the mystery fragments. We would be forced to consider that Earth possesses a recurring, perhaps still active process we do not fully understand, one that can, under different conditions, leave the same cryptic signature upon the land. The truth of the grooves is not just written in their shape, but locked within the invisible decay of atoms in the stone, waiting for us to learn how to tell time from a scratch. The stones may have a second witness, one passed down not in rock but in story. Beyond the measurements of science, there exists a vast and ancient library of human memory, recorded in the myths and legends of indigenous peoples across the globe. A startling pattern emerges when you listen to these traditions. From the high deserts of the Americas to the outback of Australia, cultures separated by oceans tell remarkably similar stories of world-altering events. They speak of great floods that drown the land, of fire raining from the heavens, and of powerful beings who the earth itself with their passage. These are not isolated tales, but a near-universal chorus. The persistence of these motifs is impossible to ignore, and it raises a profound question. Could these narratives be a form of cultural memory, a deep-time echo of the very cataclysms that carved the parallel grooves into the bedrock? It is not about taking the stories literally, but about listening for the geological truth they might symbolically preserve. When a culture speaks for generations about the Earth being reshaped by a colossal force, we should pause and consider what their ancestors might have seen. For example, certain Native American traditions recount a time when a great serpent of immense power dragged its massive body across the landscape, leaving behind deep, lasting furrows in the stone. In other parts of the world, legends describe gods or heroes plowing the land with giant tools, creating the ridges and valleys we see today. These are powerful metaphors, but metaphors for what? To a people who witnessed a continent-scouring mega-tsunami, the leading edge of that churning, debris-filled water might indeed look like a monstrous serpent moving with singular purpose. The roaring sound, the undulating motion, the way it carved the land in its wake, all could translate into the mythic image of a giant serpent's trail. Similarly, a catastrophic electrical discharge, a plasma arc from the sky touching the ground and sweeping across the horizon, could easily be remembered and described as a river of heavenly fire or the scorching breath of a sky god. These stories do not provide scientific data, but they offer something equally valuable, a human perspective on planetary trauma. They suggest that the events which shaped our physical world were so immense, so unforgettable, that they burned themselves into the collective memory of humanity, becoming the foundational legends of countless cultures. This intersection of geology and mythology is not about proving one with the other, but about recognizing a convergence of narratives. When the physical evidence in the stone points to a sudden, violent reshaping, and the oldest human stories independently speak of a sudden, violent reshaping, the coincidence becomes worthy of deep respect. It invites us to view these grooves not just as geological curiosities, but as potential bookmarks in the story of humanity itself, marking a moment so dramatic it became the backdrop for our oldest myths. The legends remind us that our ancestors were not just survivors of history, they were witnesses to the Earth's most powerful moments, and they found a way to ensure we would never forget. The search for a modern example becomes a search for a ghost. We can watch glaciers inch forward today, grinding their slow signatures into alpine valleys. We have devastating footage of tsunamis, like the one in Japan in 2011, scouring coastlines clean in moments. In laboratories, we can even fire powerful electrical arcs to etch figures into blocks of stone. Each of these processes leaves a mark that resembles, in some way, the ancient grooves we find. Yet here is the unsettling truth: not a single one of these modern events, no matter how powerful, has produced the precise parallel. continent-spanning pattern we see etched into the bedrock from Saudi Arabia to the American West. The scale is wrong. The precision is wrong. The sheer geographic distribution is completely unmatched. This absence of a clear modern is not a failure of science. It is a crucial piece of data in itself. It tells us that whatever carved these lines was not just a bigger version of the floods or storms we know. It belonged to a different category of event altogether, operating on a scale of energy and coherence that modern humanity has simply never witnessed. We are trying to understand a hurricane by studying a summer breeze. The forces involved were of a planetary magnitude, so immense that their closest comparisons might be found in the geological records of other worlds, or in the deepest chapters of our own planet's youth. This realization shifts the entire mystery. We are not looking for a process that happens every few centuries. We are likely looking at evidence of something that happens perhaps once every few 100,000 years, or even once in the entire lifetime of a species. The grooves, then, are not a textbook illustration of a common geological force. They are a monument to an extreme, a reminder that the calm and predictable Earth we inhabit is capable of moments of staggering, reshaping violence. Their very existence asks us a humbling question. How prepared is our understanding of the planet for events that lie outside the narrow window of recorded human history? This stone-carved puzzle cannot be solved by a single science. The grooves are a question asked in the language of geology, but the answer may require a conversation with the stars. To understand a mark that spans continents, we must think on a planetary scale, and that demands an unprecedented collaboration of minds. Geologists are the first detectives on the scene, meticulously analyzing the rock's composition, the microscopic stress fractures within the grooves, and the layers of sediment that cover them. Their work establishes the physical facts of the crime, but then they must call in specialists from seemingly distant fields. Glaciologists create sophisticated models of ice sheet dynamics, testing whether ancient climates could have supported continent-spanning glaciers in now arid lands. Climatologists work backwards, using chemical proxies locked in ocean sediments and ice cores to reconstruct the composition of Earth's ancient atmosphere. Searching for a snapshot of the world as it was when the grooves were made, the investigation then lifts its gaze from the Earth entirely. Astrophysicists enter the conversation with calculations of probability and celestial mechanics. They model the trajectories and impacts of near-Earth objects, calculating the staggering energy release of a miles-wide asteroid striking an ocean basin. They also consider the Sun itself, our sometimes volatile star, and the possibility of past solar outbursts of such magnitude that they could have overwhelmed Earth's magnetic shield, bathing the planet in radiation and triggering cascading atmospheric changes. This is where the interdisciplinary magic happens. By weaving these threads together, researchers can build far more robust and sometimes startling models of Earth's past. One compelling synthesis asks, could a single asteroid impact be a part key? The initial strike would generate planet-encircling megatsunamis, scouring coastlines with abrasive slurry. But the aftermath, the vast clouds of dust and vapor thrown into the upper atmosphere, could plunge the planet into a rapid, dramatic cooling. An impact winter that might trigger or accelerate glacial conditions in certain regions. In this scenario, the grooves are not evidence of one force or the other, but of a linked sequence, a 1-2 punch from the cosmos that left its signature in both rushing water and advancing ice. The parallel grooves, therefore, become more than a geological curiosity. They transform into a potential keystone, a physical clue that demands a synthesis of all our planetary knowledge. They sit at the crossroads of solid Earth, ocean, atmosphere, and even solar system science, challenging us to stop looking at our world in isolated compartments. To read this message in the stone, we must learn to speak all the languages of our planet at once, listening for the story told by the rock, the ice, the climate, and the sky in a single, unified voice. Scattered among the silent stones, we occasionally find the echoes of human hands. In a few specific and rare locations, archaeologists have documented ancient artifacts, tools, or even simple stone structures situated in close proximity to these mysterious parallel grooves. This proximity sparks a provocative side mystery. Could early human communities have discovered these naturally carved channels and seen opportunity in their smooth, linear perfection? The grooves, after all, would have provided ready-made foundations for walls, natural drainage channels for settlements, or simply convenient pathways across a rugged landscape. It is a logical and practical idea that our ancestors recognized and utilized a pre-existing geological feature, much as we might build a house beside a river or a road along a valley. This view sees the grooves as a convenient canvas, later painted upon by human activity, but a more speculative question lingers. Do any of these grooves show patterns that go beyond mere utility? Are there alignments, clusters, or modifications that hint at something more intentional, perhaps even ceremonial? A handful of independent researchers have pointed to sites where the direction of the grooves seems to align with solstice sunrises or significant stars, or where the grooves themselves appear to have been subtly enhanced or connected by human-placed stones. To the vast majority of mainstream archaeologists and geologists, these instances are almost certainly coincidence, the product of our pattern-seeking minds overlaying meaning onto random natural formations. The Earth is vast, and the chance alignment of a natural groove with a celestial event is statistically inevitable somewhere. Yet, the coincidence itself is deeply thought-provoking. It forces us to consider the timeline not just of the rock, but of us. If a global catastrophe, whether from water or ice or sky, did carve these grooves within the span of human development, what did that mean for our ancestors? The grooves would then be more than a geological curiosity. They would become a potential stratigraphic marker, a dividing line in the soil of human prehistory. Imagine a layer of sediment worldwide, beneath which we find one kind of human artifact, and above which we find another, with the groove-carved bedrock forming the boundary. Such a discovery would revolutionize our understanding of human resilience. It would suggest that scattered bands of early humans not only witnessed a planet-reshaping event, but survived it, and their world, their very ways of life, were fundamentally altered in its aftermath. The grooves, in this light, transform from a passive scratch into an active character in the human story. They become the silent witness to a generation that looked upon the fury of the earth or the heavens and lived to tell the tale, perhaps encoding that memory into the very myths we explored earlier. This connection, however tenuous, reminds us that our history is not separate from the planet's history. We are not just observers of these ancient mysteries, we are the descendants of those who may have walked among them, forever shaped by the forces that carved straight lines into the foundation of the world. For centuries, the full scale of these grooves remained hidden beneath forests and sand. Our understanding was limited to what we could walk up to and touch, a handful of exposed sites that hinted at a larger mystery. Today, that limitation has vanished. We are no longer earthbound detectives. We have been given eyes in the sky and X-ray vision for the planet itself. The key to this new perspective is a technology called LIDAR, which stands for light detection and ranging. Imagine flying over a dense, uncharted rainforest or a rugged desert plateau. A LIDAR unit, mounted on an aircraft or drone, fires millions of tiny laser pulses at the ground below. Each pulse bounces back, and by measuring its return time, a computer builds an astonishingly precise three-dimensional map of the surface. The true magic happens next. Software can digitally strip away every single tree, every bush, every blade of grass, revealing the bare ground beneath as if the landscape had been shaved clean. What emerges from this digital deforestation are landscapes we never knew existed. In places like the dense jungles of Central America or the overgrown hills of the Mediterranean, LIDAR has revealed vast, previously unknown networks of these parallel grooves. Etched into bedrock that has been invisible to human eyes for 10,000 years. It is like pulling back a colossal green carpet to find a message carved into the floorboards of the continent. Each new discovery adds another data point to the global map, transforming isolated curiosities into a coherent, widespread pattern. This aerial reconnaissance extends far beyond LIDAR's laser focus. High-resolution satellite imagery now allows a single researcher, sitting at a computer, to scan thousands of square miles of the most remote and hostile terrain on Earth. The scorching emptiness of the Sahara Desert, the frozen expanse of Antarctica, the high plateaus of the Andes, these are no longer barriers to exploration. With satellite data, scientists can identify potential groove sites, trace their directions across impossible distances, and even make preliminary measurements, all without ever setting foot in the field. They can compare a site in Saudi Arabia with one in Namibia, side by side on the same screen, looking for similarities in spacing, orientation, and morphology that would have been impossible to confirm a generation ago. This is not just about finding more grooves, it is about seeing the connections between them. It turns a collection of local mysteries into a single, planetary-scale puzzle. The final piece of this technological triad is the software that makes sense of it all: Geographic Information Systems, or GIS. Think of GIS as a digital detective's bulletin board, but one that spans the entire globe. Researchers can upload every groove they find via LIDAR and satellite, plotting each one as a line on a vast interactive map. Then, the real analysis begins. The software can calculate the predominant direction of every groove in North America, then compare that vector field to the pattern emerging from Africa. It can analyze density, looking for hotspots where the grooves are most concentrated. It can overlay this data with other layers of information: ancient coastlines from millions of years ago, known impact crater locations, models of historic ice sheet flow. By visualizing all this information together, patterns emerge that the human eye could never perceive from ground level. Perhaps all the grooves in a region point radially away from a now dry inland sea. Maybe they align in bands that correspond to the theorized path of a mega tsunami across a continent. GIS provides the first real opportunity to move from storytelling to statistical, evidence-based modeling. It is transforming the grooves from a geological folklore into a quantifiable, testable planetary phenomenon. This flood of new data is creating the first comprehensive global dataset. What was once a series of intriguing anecdotes shared between specialists is now becoming a solid body of evidence open to systematic, rigorous study. For the first time, researchers can ask big, bold questions with the tools to seek answers. Does the global directional data support a single source event or multiple ones? Is there a correlation between groove locations and specific geological features, like fault lines or ancient shorelines? The technology does not give us the answers, but it finally gives us the language to frame the questions properly. We are no longer just looking at strange marks on a few rocks. We are beginning to see the outline of a shadow, a ghostly impression of a force that passed over the Earth, captured in stone and now, finally, revealed in data. The mystery is not being solved by these tools. It is being precisely defined, measured, and inviting us to look deeper than we ever thought possible. The scientific journey to understand these grooves is not a quiet one. It unfolds in a vibrant, often passionate arena of academic debate, where the very nature of geological evidence is contested. This is the state of the field today, a dynamic and healthy controversy that fuels deeper investigation. On one side, the prevailing view within mainstream geology is one of caution and locality. This polygenetic perspective argues that the grooves likely have multiple origins. The marks in Canada, they say, are almost certainly glacial. The channels in a desert wadi might be the result of rare, catastrophic flash floods. The lines on a coastal plateau could be from wave action during a past sea level high. In this view, attributing every single groove worldwide to one cause is an oversimplification, ignoring the incredible diversity of Earth's processes. It is a stance built on razor, the principle that the simplest explanation, using known and observable forces, is usually the right one. Proponents point out that nature is inventive, and similar effects can arise from wildly different causes. A unified global catastrophe, while dramatic, is not the first tool they reach for. This cautious approach is challenged directly by a growing chorus of catastrophist researchers. They argue that the similarities between grooves on different continents are too precise to be coincidence. The consistent parallelism, the specific depth and morphology, the way they appear on similar types of bedrock, all point toward a single, unifying cause. For them, invoking a dozen different local mechanisms to explain an identical global pattern is the more complex, less elegant solution. They contend that mainstream geology, shaped by a century of uniformitarian thinking, the idea that the present is the key to the past, may be inherently biased against considering truly rare, high-energy planetary events. The debate is not merely philosophical, it is intensely practical, fought over the details of specific field sites. At a conference or in a peer-reviewed journal, you might see a heated exchange over the mineralogy of a friction melt layer. One researcher presents data showing trapped oceanic microfossils within the glass, claiming proof of a tsunami's abrasive slurry. Another counters that the chemical signature indicates only local rock, consistent with glacial grinding. A third might question the dating methodology itself, suggesting the cosmic ray clock was reset by a later event. This back and forth is not a sign of failure, it is the essential engine of scientific discovery. It forces every side to sharpen their arguments, seek more robust evidence, and refine their models. The mystery persists not because scientists are ignoring it, but because the evidence, for now, remains tantalizingly ambiguous. No single narrative has yet presented a knockout blow, a piece of data so conclusive that it compels the entire field to shift its view. This ongoing debate is a testament to the groove's power. They are a puzzle that refuses to be solved with the tools of any single geological sub-discipline. They demand a humility, an openness to the possibility that our planet's history contains chapters of drama we are only beginning to read. The stones have asked a profound question, and science, in its best tradition, is arguing its way toward an answer. The stone's ancient message may hold a key to our future prosperity. This is where the mystery of the grooves moves beyond academic debate and touches the practical world of water, minerals, and modern survival. The immense forces that carved these parallel lines, whether ice, water, or something else, did not just leave a signature, they often left a gift. These events acted as planetary-scale sorting machines, gathering and concentrating valuable resources along their paths. Understanding the grooves, therefore, is not merely an intellectual exercise, it can be a treasure map. Consider the well-understood process of a glacier. As it slowly grinds forward, it does not just pulverize rock, it acts like a colossal, slow-motion gold panner. The ice carries a mixture of everything it has scraped up, from fine silt to boulders. When the glacier eventually retreats, it leaves behind distinct layers of this material, called glacial till. Within that till, heavier, denser minerals like gold, diamonds, or rare earth elements can become concentrated in rich deposits known as placer deposits. Prospectors have followed these glacial trails for centuries. Now imagine if a catastrophic mega-tsunami produced a similar, but far more rapid and violent, sorting effect. A wave of that magnitude, churning with debris, would not deposit its load gently. It would create sudden, thick layers of sediment, potentially trapping and concentrating minerals in specific patterns related to its flow. If the grooves are indeed the scratch marks from such an event, then the direction they point could lead us to sedimentary basins or ancient shorelines where valuable resources were laid down in a geological instant. The grooves become directional arrows, pointing not just to the past, but to potential wealth hidden below. This practical connection extends to the most vital resource of all, water. The grooves themselves are physical channels etched into the bedrock. In many arid regions, these ancient trenches can control the modern movement of groundwater. They can act as natural pipelines, directing subsurface flow along their length, or they can create barriers that trap water in porous layers. For communities living in drylands, identifying and mapping these groove systems could reveal hidden aquifers or show where to drill a well with a much higher chance of success. Furthermore, on the surface, the linear depressions often collect wind-blown soil and debris over, creating subtle fertile strips in an otherwise barren landscape. They can guide the flow of rare rainfall, concentrating moisture and nutrients, which in turn influences where plants grow and where animals graze. An ancient cataclysm, in this light, may have inadvertently sculpted the blueprint for life in some of Earth's harshest environments. This transforms the entire pursuit from a mystery into a tool. For a mining geologist, a clear understanding of whether a set of grooves is glacial or tsunami formed dictates an entirely different exploration strategy. One points you toward moraines and outwash plains, the other might direct you to investigate sedimentary sequences far from any ancient ice. For a hydrologist planning a community's water security, knowing that a network of grooves functions as a groundwater conduit is critical information. It affects where you place wells, how you manage potential contamination, and how you understand the recharge of the aquifer. even for urban planners and engineers, recognizing that a development site is crisscrossed by these ancient linear features is vital. They could indicate zones of differential erosion, areas where the bedrock is pre-fractured, or pathways that could channel floodwaters in unexpected ways during an extreme storm. So the silent lines in the stone speak to us on multiple levels. They are a riddle from our planet's dramatic past, a potential archive of human memory, and a practical guidebook to the resources that lie beneath our feet. Decoding their origin ceases to be a purely historical question. It becomes an act of modern resource intelligence. By listening to what the grooves tell us about the forces that made them, we learn not only how the Earth was shaped, but how to live more wisely upon it. The search for answers, then, is driven by more than curiosity. It is fueled by the need to sustainably navigate our future on a planet that still holds profound and useful secrets from its turbulent past. This quiet, patient Earth we walk upon is a comforting story. For 200 years, the guiding principle of geology has been uniformitarianism, a simple but powerful idea that the present is the key to the past. It tells us that the mountains, canyons, and valleys we see were sculpted by the same slow, observable forces we witness today. The gentle drip of water, the steady grind of ice, the patient push of tectonic plates. All operating over unimaginably vast stretches of time. This view gives us a sense of planetary stability, a deep-time reassurance that change is measured and predictable. It frames our world as a gradual home. Yet the parallel grooves etched across continents whisper a different, more unsettling narrative. They are a physical argument for catastrophism, the idea that our planet's history is not a smooth, uninterrupted line, but a story punctuated by sudden, violent, high-energy events that can rewrite the landscape in a single day. If these lines were carved by a globe-spanning tsunami or a celestial electrical discharge, then uniformitarianism, while explaining 99% of geology, misses the critical 1% that changes everything. It would be like studying a calm forest to understand a meteor impact. The grooves force us to confront a profound philosophical shift, not just in how we read rocks, but in how we see our place on this planet. Embracing this possibility does more than update a textbook. It reshapes our fundamental perception of home. We are accustomed to thinking of Earth as a stable stage, a reliable backdrop against which the drama of life unfolds. But what if the stage itself is prone to sudden, dramatic rearrangement? Accepting that catastrophes of planetary scale are woven into our world's fabric introduces a humbling dose of cosmic perspective. It suggests that the calm periods we inhabit, the of relative climatic peace, may be the exception, not the rule. These quiet eras are the precious interludes between planetary upheavals. The grooves, therefore, become more than geological features. They are temporal markers, dividing lines in deep time that separate one world from the next. They hint that the planet we know today, with its familiar continents and climates, is merely the latest version, a snapshot following the last great reset. This challenges a very human instinct to see our current environment as permanent and default. It reminds us that we are not living on a finished product, but on a work in progress, one capable of sudden, breathtaking revisions. This reckoning extends beyond rocks to the very story of life itself. If Earth's physical face can be remade in an instant, what does that mean for the biological clock? Major extinction events in the fossil record, like the disappearance of the dinosaurs, have long been suspected ties to catastrophic triggers, such as asteroid impacts. The global grooves offer potential physical evidence of mechanisms powerful enough to cause such widespread biological turnover. A continent-scouring mega-tsunami would not just carve stone, it would devastate ecosystems, alter coastlines, and dramatically shift climates in its aftermath. An atmospheric electrical event of sufficient scale could have triggered wildfires, altered atmospheric chemistry, and caused widespread loss of life. In this light, the grooves are not silent scratches. They are potential signatures of the very events that have acted as evolutionary bottlenecks, wiping the slate clean and allowing new chapters of life to begin. They suggest that the rise and fall of species, the branching of the tree of life, may be intimately tied to these rare but recurring planetary convulsions. Our own existence, then, might be a direct consequence of survivors who endured the aftermath of such an event, adapting to a world freshly and transformed. Ultimately, the mystery of the parallel grooves invites us into a deeper, more dynamic relationship with our planet. It asks us to exchange a view of Earth as a slow and steady machine for one that recognizes its capacity for both profound patience and sudden, creative violence. This is not a cause for fear, but for a more mature understanding. It means viewing the ground beneath our feet not as an inert foundation, but as an archive of epic stories, most of them slow and patient, but a few written in the frantic, urgent script of catastrophe. Recognizing this duality makes our home world more fascinating, more resilient, and more real. It teaches us that stability is a gift, not a guarantee, and that the forces which shape continents are also the forces that shape the conditions for life. To solve the riddle of the grooves is to learn a new way of reading our planet's autobiography, one where we accept that the most dramatic sentences are often written in the shortest, most explosive bursts of time, leaving marks so clear and so strange that we are only now beginning to understand the language in which they are written. A definitive culprit for such a planetary event has proven frustratingly elusive. If a globe spanning tsunami carved these grooves, we are left with a fundamental question: where is the gun that fired the shot? A wave of that magnitude demands a trigger of almost unimaginable energy, and the hunt for that trigger has become a parallel scientific quest. One that scours the deepest ocean floors and the oldest layers of rock. The most obvious suspect is a colossal asteroid or comet striking an ocean basin. The impact would vaporize billions of tons of water and rock, sending a series of mega-tsunamis racing across the world's oceans. But for this to explain the grooves we see, we need to find the crater, and it must be from the right time. The most famous impact crater on Earth, buried beneath the peninsula, is a compelling candidate in terms of sheer power. Its creation 66 million years ago is linked to the extinction of the dinosaurs and certainly generated devastating global tsunamis. Yet, this event is far too ancient. The geological dating for many of the parallel grooves, especially those possibly linked to human memory, points to a much more recent, within the last few 100,000 years, not tens of millions. Is a dramatic precedent, but it is not our culprit. The search then turns to the ocean itself, to catastrophic collapses of the, we know these happen. Just 8,200 years ago, a massive submarine landslide off the coast of Norway, known as the Slide, sent a tsunami crashing into the coastlines of Scotland and Norway. The evidence is clear in the geological record, with sediment deposits and drowned landscapes. But while the event was regionally catastrophic, its effects were not global. The scale, while immense, does not match the continent's scouring power implied by grooves found in the interiors of multiple landmasses. It was a powerful regional event, not a planetary one. This leaves researchers with a puzzling gap. They have a compelling hypothesis, a global tsunami, and a clear mechanism for how it could carve the grooves. Yet the specific event that could have set it all in motion remains hidden, perhaps still undiscovered on the dark ocean floor or misinterpreted in the geological column. Some scientists propose we may be looking for not one gun, but an entire arsenal. Instead of a single, colossal impact, perhaps Earth passed through a dense cloud of cometary debris, suffering a storm of smaller impacts across several centuries, or each impact could generate a significant regional tsunami, and the cumulative effect over time, as sea levels fluctuated and climates shifted, might create a mosaic of grooves at slightly different times. Yet all within a broader catastrophic window. Another possibility shifts the trigger from the sky to the Earth's own fiery interior. The eruption of a supervolcano, like the one that formed Yellowstone caldera, can be so violent it triggers secondary effects, including the collapse of volcanic flanks into the sea or the sudden release of vast subglacial lakes, each capable of generating immense waves. A period of intense global volcanism could have set off a cascade of tsunamis, a rolling series of disasters that left their marks around the world. The lack of a single, definitive trigger is not necessarily a flaw in the catastrophic hypothesis, but rather its greatest challenge and its most intriguing frontier. It forces a broader perspective, asking us to consider that our planet's most dramatic moments may come from a convergence of disasters. A perfect storm of celestial and terrestrial violence whose combined signature is written in the parallel lines upon the stone. The force that could carve such lines would not stop at the stone. It would rewrite the sky. Any event with the power to machine grooves across continents would unleash a cascade of secondary effects, a planetary chain reaction that fundamentally alters the climate itself. Think of it not as a single strike, but as the first domino in a sequence that reshapes the world for. A mega tsunami of the scale we have discussed is more than a wave, it is a climate engine. As it rages across landmasses, the colossal energy transfer vaporizes billions of tons of seawater, hurling it into the upper atmosphere. This is not ordinary evaporation. It is a sudden, violent injection of moisture on a global scale. The immediate aftermath could be a period of intense, worldwide rainfall, a deluge that lasts for years, fundamentally altering erosion patterns and plant life. But the longer-term effect might be even more dramatic. All that water vapor, along with the immense clouds of dust and debris scoured from the continents, would form a thick, sun-blocking veil around the planet. Sunlight would be reflected back into space, and global temperatures would plummet. Scientists call this an impact winter, a rapid cooling event typically linked to asteroid strikes. In this scenario, the grooves are the scratch from the impact, and the ice age that follows is the planet's feverish response. The climate forcing becomes a self-fulfilling prophecy. The catastrophic event creates the very conditions, widespread cooling and increased precipitation, that allow ice sheets to form and advance in regions where they could not exist before. Suddenly, the glacial evidence we find near some grooves makes a terrifying new kind of sense. The ice did not make the grooves. The event that made the grooves made the ice. This turns the traditional explanation completely on its head. The glacial theory becomes not the cause, but a consequence, a later chapter in a story that began with fire and flood. The grooves are the initial signature, the fresh wound, and the advancing glaciers are the planet's slow, icy scar tissue forming over it. This blurring of cause and effect is where the mystery achieves its deepest complexity. We are not looking at a single moment in time, but at a ripple effect through Earth's systems. An electrical discharge hypothesis suggests a different, but equally profound, climate pathway. A planet-spanning plasma event would do more than fuse rock. It would rip apart the very molecules of the atmosphere. The intense heat and radiation could break apart nitrogen and oxygen, allowing them to recombine into nitrogen oxides. These compounds are powerful greenhouse gases in some contexts, but they can also lead to the destruction of the protective ozone layer and the creation of widespread smog, again altering how sunlight reaches the surface. The chemical fallout could poison oceans and trigger acid rain, devastating ecosystems and potentially shifting global weather patterns in unpredictable ways. The climatic chaos that follows, whether a rapid cooling or a toxic atmospheric shift, could then stress the biosphere to its breaking point, creating the environmental preconditions for a glacial advance or a mass extinction. This perspective forces us to see the grooves not as an isolated puzzle, but as the keystone in a vast, interconnected arch of Earth's history. They are the tangible evidence of the match that lit the fuse. The climate changes, the extinctions, the advance of ice, and even the birth of new ecological niches, all could flow downstream from that one catastrophic ignition point. To understand the lines in the stone, we must also read the echoes they left in the ancient air and the deep ocean sediments, a unified story of a planet violently adjusting to a new reality. The most thrilling story is not always the true one. As we stand before these silent, enigmatic lines, surrounded by competing narratives of ice, water, and fire from the sky, a vital discipline must guide us. It is the discipline that separates compelling speculation from verifiable fact. This is where the true work of science begins, not with choosing the most exciting idea, but with putting every idea, no matter how conventional or radical, to the same unforgiving test. The principle is straightforward: extraordinary claims require extraordinary evidence. A theory about a planet-spanning cataclysm is, by definition, an extraordinary claim. It cannot stand on a pattern alone, no matter how widespread or precise that pattern appears. It must make predictions. It must tell us, if I am true, then you will find X, Y, and Z in the world. These predictions become the roadmap for investigation, a checklist against which we measure reality. For the glacial theory, the predictions are well established and often met in classic regions. If a glacier carved these lines, we should find the glacial till it left behind, the distinctive U-shaped valleys and other marks of ice flow in the immediate vicinity. The absence of this supporting evidence in deserts is precisely what created the mystery in the first place, challenging the theory's universal application. Now we must apply the same rigorous logic to the catastrophic alternatives. If a mega-tsunami of continental scale was the artist, its signature would be written in more than just scratches. The prediction is clear. We should find a specific, synchronous layer in the geological record around the world. This layer would be a deposit of sediment, chaotic and full of debris, laid down in a single, violent event. It might contain a mix of deep ocean microfossils and terrestrial material, all churned together and dropped far inland. This layer should appear at the same depth in cores taken from ancient lake beds, ocean floors, and ice sheets, all pointing to the same moment in time. Finding that global layer would be the smoking gun, the extraordinary evidence for an extraordinary event. Conversely, the electrical discharge hypothesis makes its own distinct predictions. If a cosmic plasma arc seared these grooves into the bedrock, the evidence would be written in the atomic structure of the stone itself. The prediction focuses on the melted glaze sometimes found within the grooves. This material should carry a unique isotopic fingerprint, a chemical signature indicating instantaneous, extreme heating from an atmospheric source rather than gradual friction. It might show patterns of magnetization that align with the direction of the groove, as if the rock's magnetic minerals were flash-frozen in alignment with the passing energy. Furthermore, if such an event occurred, it could have altered the chemistry of the ancient atmosphere in ways that left traces in ice cores or sedimentary layers, another testable prediction. The path forward, then, is not a debate of stories, but a meticulous process of checking these lists. It requires geologists to be detectives, not advocates. They must go into the field with open minds and specific questions. When they take a core sample from a dry lake bed in Arizona, they are not just looking for sediment, they are testing for the tsunami layer. When they analyze a sliver of glassy rock from a groove in Saudi Arabia under a mass spectrometer, they are not just identifying minerals, they are hunting for that unique isotopic signature. This work is slow, expensive, and often unglamorous. It does not provide the instant satisfaction of a grand unified theory, but it is the only way to build knowledge that lasts. The history of science is littered with beautiful ideas that collapsed under the weight of contradictory evidence, and with dismissed notions that were later vindicated by a single, undeniable discovery. The fate of the parallel grooves will be decided not by which story captures our imagination, but by which one survives this relentless, evidence-based interrogation. Our role as observers is to appreciate the mystery while respecting the method, to enjoy the speculation while valuing the slow, careful accumulation of proof that will one day, we hope, turn this captivating question into a settled chapter in Earth's epic story. These silent lines in stone offer more than answers, they offer a profound way to learn. At its heart, this mystery is in how science actually works, transforming abstract textbook principles into a tangible, global puzzle. For a student first encountering geology, the parallel grooves serve as a perfect gateway. They are a physical phenomenon that immediately raises the most fundamental questions. How is rock shaped? What forces are powerful enough to leave a lasting mark? To seek answers, one must first understand the basic vocabulary of the Earth. The investigation naturally leads into lessons on erosion, the difference between mechanical grinding and chemical weathering. It introduces the immense scale of glaciation, the concept of continental ice sheets, and the clues they leave behind. It touches on plate tectonics, as the very locations of the grooves on now separated continents hint at ancient geographies. Each geological concept ceases to be a fact and becomes a necessary tool in a much larger investigation. But the true educational power lies not in presenting settled facts, but in showcasing the scientific method in real time. Here is a real-world problem with no answer key in the back of the book. Students are invited to step into the role of the researcher. They can examine the same evidence the experts debate, the groove morphology, the directional data, the microscopic mineralogy. They can then evaluate the competing hypotheses, weighing the strengths and weaknesses of the glacial theory against the mega-tsunami model or even the more speculative electrical idea. This process teaches critical thinking in its form. It demonstrates that scientific knowledge is not a static list of truths handed down, but a dynamic, self-correcting process built on observation, hypothesis, testing, and most importantly, rigorous debate. Students learn that disagreement among scientists is not a sign of failure, but the essential engine of discovery, pushing each side to find stronger evidence and build more robust models. The grooves become a global classroom without walls, accessible through images, maps, and datasets. A classroom in Arizona can collaborate with one in Sweden, comparing local bedrock features and discussing whether they see evidence for a local event or a global one. This tangible connection to a planet-wide phenomenon fosters a sense of scale and interconnectedness that a standard curriculum often struggles to convey. It makes Earth science immediate and urgent. Furthermore, the mystery inherently inspires curiosity about our planet's deep past. It challenges the assumption that the world has always looked as it does now, opening minds to the reality of profound change over time. It encourages learners to look at their own local landscape with new eyes, to ask what stories the rocks might tell if they knew how to listen. Ultimately, this engagement teaches a lesson far beyond geology. It shows that science is a story we are still writing. The grooves demonstrate that some of the most fascinating chapters in our planet's history remain provisional, filled with questions that demand fresh thinking and new perspectives. This understanding cultivates intellectual humility and resilient curiosity. It prepares a new generation not just to accept explanations, but to participate in the never-ending quest for them. To understand that the next great discovery might lie in re-examining a line carved in stone that everyone else has simply walked past. In this way, the mystery does more than teach about the Earth. It teaches us how to think about the world, embracing uncertainty not as an obstacle, but as the very space where true learning begins. The next chapter of this story will be written not with theories, but with data. A mystery of this scale demands a coordinated, global response from the scientific community, and several clear paths forward have emerged as top priorities. The most urgent need is for a definitive timeline. Individual dating efforts at scattered sites have given us a frustrating range of possibilities. What is required now is a coordinated global dating project, treating the grooves as a single planetary phenomenon. Imagine teams of researchers across continents using the same cutting-edge techniques, cosmogenic nuclide dating, and advanced luminescence methods on samples collected under identical protocols. The goal would be to answer one pivotal question: did these events happen simultaneously around the world, or are we looking at separate episodes scattered across millions of years? A synchronized chronology would either make the case for a single cataclysm undeniable or force us to confront a recurring planetary process we have yet to name. Equally critical is a forensic analysis of the stone itself. We need a detailed, comparative geochemical study of those glassy glazes found inside the grooves, from the American Southwest to the Arabian Peninsula to the Australian outback. Are their chemical signatures identical, suggesting a common formation process under the same extreme conditions? Or do they vary in ways that point to different abrasive agents, like tsunami slurry versus glacial grit? This is like comparing the residue from a crime scene found in different countries, looking for a match that ties them all to the same weapon. Advanced spectrometers can now detect isotopic ratios and trace elements invisible to the naked eye, potentially revealing whether the melting was caused by friction, by the heat of a hyper-concentrated debris flow, or by a sudden atmospheric energy discharge. The truth is encoded in the chemistry. Alongside field evidence, we must leverage the power of simulation. Improved computer modeling can serve as a virtual testing ground for each hypothesis. Climatologists and glaciologists can create ever more refined models of ancient ice sheet dynamics, asking with greater precision whether ice could have feasibly advanced into now arid regions under past climate configurations. At the same time, oceanographers and geophysicists can run sophisticated models of mega-tsunami propagation. They can input data from potential trigger events, like a specific asteroid impact location or a massive submarine landslide, and simulate how the resulting wave would travel across ancient ocean basins, where it would make landfall and with what force. These digital experiments can predict where the deepest scouring should occur and what directional patterns the grooves should follow, giving field researchers a map of where to look next for corroborating evidence. Ultimately, the Earth itself still holds undiscovered pages of this story. Continued field exploration in understudied and inaccessible regions is paramount. Vast areas of Central Asia, the deep Amazon basin, and the interior of Antarctica remain geological frontiers. Each new groove field discovered, especially in these blank spots on the map, adds another piece to the global puzzle. A newly found network in Mongolia, for instance, could reveal a flow direction that perfectly points toward an ancient inland sea. A set of grooves on an isolated plateau in South America might show a unique pattern that rules out local glacial activity. Every expedition carries the potential for a discovery that suddenly makes the scattered pieces click into a coherent picture. This is why the mystery of the parallel grooves is far from a closed case. It is an open invitation. It calls not for speculation, but for a new generation of geologists, geochemists, modelers, and explorers to collaborate across borders and disciplines. The lines are there, waiting in the stone. The tools and the questions are now in our hands. What we choose to look for next will determine whether these ancient scratches remain a fascinating enigma or become the key that unlocks a forgotten chapter of our planet's most dramatic day. The story of these grooves is a global one, and solving it will take a global community. Professional researchers cannot possibly survey every remote plateau, desert basin, or forested hillside on Earth. This is where the power of collective curiosity becomes not just helpful, but essential. Anyone with an inquisitive mind and access to the internet can now join the search from their own home. The tool is as simple as it is powerful: satellite imagery platforms like Google Earth. These virtual globes place a detailed map of the entire planet at your fingertips, allowing you to scan landscapes that would take weeks of arduous travel to reach in person. The task is straightforward, yet thrilling. You are looking for patterns, for long, straight, parallel lines etched into the bedrock, especially in regions far from known glaciers. They might appear as subtle tonal differences, like faint scratches on a giant stone canvas, or as more pronounced ridges and channels running side by side across miles of terrain. If you spot something that looks promising, the next steps are simple but vital. Note the precise coordinates. Take a screenshot that captures the scale and context of the feature. Then you can share your find with universities or research organizations that are actively cataloging these phenomena. Your observation could be the lead that sends a field team to a previously unknown site, adding a critical new data point to the global map. This is the heart of modern citizen science, transforming passive interest into active participation. Your keen eye, from thousands of miles away, becomes an extension of the scientific process. But public engagement goes beyond just looking at screens. Hikers, backpackers, and pilots in small aircraft often venture into places few others ever see. If you are out in the wilderness and come across a rock surface covered in strange, parallel lines, you are standing on a potential piece of the puzzle. Document it with your phone's camera, capturing wide shots to show the overall pattern and close-ups to reveal the texture and depth. Even noting the general direction the lines seem to point can be valuable information. By sharing these field observations, you provide ground truth, the real-world confirmation that turns a curious satellite image into a tangible geological feature. This collective effort does more than just gather data. It builds a wave of public interest that is crucial for any long-term investigation. Widespread fascination drives funding for more sophisticated research, from advanced satellite surveys to costly mineralogical analysis. It encourages media coverage that reaches other potential contributors, creating a virtuous cycle of discovery. When thousands, or even millions, of curious people around the world are all looking at the Earth with a detective's eye, we exponentially increase the odds of finding that one crucial clue. The site with the perfect layer of sediment or the unmistakable chemical signature that finally tells us what passed over our planet and left its mark for us to find. You are not just watching a mystery unfold, you are invited to become a part of solving it. Our planet is not the only world that bears these strange, linear scars. To truly understand the forces at work, we must lift our gaze from Earth and look across the solar system, where other rocky and icy bodies tell their own stories in stone and ice. On Mars, orbiting probes have sent back images of landscapes that feel hauntingly familiar. The red planet is etched with vast networks of channels and grooves, many running in strikingly parallel formations. For decades, planetary scientists have interpreted these as the work of ancient water catastrophic floods that burst from underground reservoirs and raged across the Martian surface. Or perhaps from long-vanished glaciers. The similarities to features like our own channeled Scablands are impossible to ignore, suggesting that the same basic physics of catastrophic fluid flow operates across the cosmos. Then there are the icy moons. Look at Jupiter's moon Europa, a world encased in a shell of water ice. Its surface is a cracked and fractured tapestry, crisscrossed by long, linear ridges and grooves that stretch for hundreds of miles. These are often explained by the tidal forces of Jupiter's immense gravity, flexing the moon's crust and causing the ice to fracture and shift over eons. In each case, whether on Mars or Europa, scientists propose a specific, local cause: water here, ice dynamics there. But this celestial perspective forces a profound question back upon our own mystery. Could the process that carved Earth's grooves be something more fundamental than a one-time catastrophe, a type of planetary signature that appears under different guises across the universe? Perhaps these parallel lines are not about a specific agent like ice or water, but about the behavior of any thick, flowing medium, whether it is a glacier, a tsunami slurry, or even a convecting ice shell. When it moves with enough power and coherence across a solid surface, the physics of flow and erosion may create similar patterns anywhere in the cosmos given the right conditions. This reframes our entire investigation. Understanding Earth's grooves is no longer just about solving a historical puzzle. It becomes a vital piece of comparative planetology, the science of understanding how planets and moons evolve by comparing their features. If we can definitively determine what carved our lines, we gain a powerful diagnostic tool. We could look at a newly discovered groove on Mars and say, with greater confidence, this was carved by a catastrophic flood, not by a slow-moving glacier. It turns our mystery into a stone for interpreting the history of other worlds, but the learning flows both ways. By studying the extreme environments of our solar system, we might discover models we have never seriously considered for Earth. What if the linear fractures on Europa, caused by tidal stresses in an ice shell, have a terrestrial counterpart in Earth's own crust during periods of immense tectonic or gravitational stress? Could some grooves be the fossilized remnants of the planet's crust itself stretching and fracturing on a continental scale? The solar system becomes a vast laboratory, showing us the incredible diversity of ways a planetary surface can be marked. This elevates the humble groove from a terrestrial curiosity to a cosmic cipher. It suggests that the lines written into our bedrock are part of a universal language of planetary change. By learning to read them here, we are not just uncovering our own past, we are developing the vocabulary to ask better questions about the history of every world we see. The search for answers on Earth becomes intrinsically linked to our quest to understand our place in a wider, dynamic family of planets, all bearing the scars of their own unique stories. Granite and limestone hold memories longer than any book. This is the profound resilience of bedrock, the planet's ultimate archive. While the world above it is in constant motion, with rivers changing course and civilizations rising and falling, the solid foundation beneath remains a patient, silent witness. Bedrock is not just rock, it is the Earth's skeleton, the final layer before the mantle's heat. Its very nature is to endure. When an immense force passes over it, whether the slow grind of ice or the sudden rage of a cataclysm, the bedrock does not simply erode away like sand. It registers the event. It accepts a signature. The parallel grooves we find are not superficial scratches. They are inscriptions carved directly into the planet's most durable medium. Think of them as paragraphs in a stone autobiography, written in a language of force and friction. This permanence is why we can find these lines in places like the Mojave Desert, where scorching days and freezing nights have weathered the surface for millions of years. The grooves persist. Wind scours them, dust fills them, but the fundamental mark remains, a ghostly impression refusing to fade. Their very survival against the relentless agents of erosion is a clue in itself. It tells us the marking force was not a gentle one. A faint stream or a mild wind could never leave a lasting impression here. Only something of staggering power could etch a message so deep that time itself struggles to erase it. This transforms our perspective. We are not looking at a temporary feature, but at a permanent entry in the planetary ledger. The bedrock has faithfully recorded a transaction of energy so vast it became a permanent part of the landscape. Deciphering this record is our act of deep listening. It is how we hear the planet's history, a history narrated not in words, but in the enduring scars left upon its bones. Perhaps the truth of the grooves lies not in choosing one story, but in weaving several together. After this deep examination of the evidence, from the desert's defiance to the power of water and the whispers of myth, we must ask if a single, unified theory is even possible. The human mind craves a neat answer, a solitary villain for the mystery. Yet Earth's history is rarely so simple. Its narratives are layered, complex, and often messy. What if the solution is not a choice between ice and water, but a sequence that involves both? Consider a hybrid model, a synthesis of the most compelling evidence. Imagine a primary, global catastrophe, such as a colossal asteroid impact in an ancient ocean. This event unleashes the planet-scouring mega-tsunamis we have discussed, their churning, abrasive slurry carving the initial, precise parallel grooves into bedrock across continents. This is the first and most violent inscription, but the story does not end there. The aftermath of such an impact, the dust and vapor thrown into the stratosphere, triggers a rapid global cooling, a dramatic climate shift. This new, colder world allows ice sheets to form and advance in regions that were once temperate. Now, as these glaciers grow and flow, they encounter the pre-existing grooves. The ice with its embedded debris does not create new lines from scratch. Instead, it flows into these ancient channels, following the path of least resistance. Over centuries, the glacial grinding acts like a slow, persistent craftsman, widening, deepening, and polishing the grooves that were already there. In this view, the grooves are a geological palimpsest. That is an ancient manuscript where the original writing was scraped away to make room for new text, but where faint traces of the older, underlying message still show through. Here, the bedrock is the parchment. The first, catastrophic event writes the clear, straight lines in a frantic global hand. Later, slower processes, like glaciation or even wind and water erosion, overwrite parts of the message, modifying it, making it fainter in some places and more pronounced in others. This hybrid model elegantly acknowledges the strengths of multiple hypotheses. It explains the global distribution and precise parallelism that so strongly suggest a single, violent cause. Yet it also accommodates the clear glacial evidence found in some regions, not as the originator, but as a subsequent modifier. It resolves the puzzling timeline discrepancies by allowing for a primary ancient event, with later ice ages reactivating and reshaping the old wounds. The search for one single cause may be a beautiful simplification, but the Earth specializes in complex narratives. The grooves, then, are not a riddle with one answer. They are a cumulative record, a stone tape that has recorded multiple chapters of planetary change. The clearest, most consistent signal etched into that tape, the foundational layer, points to a moment of unimaginable violence. The fainter, more localized modifications tell the story of what came after. Accepting this complexity is not a surrender, but a step toward a richer understanding. It means listening to the stone with more nuanced ears, hearing not just one voice from the past, but a chorus of events, each leaving its distinctive mark upon the enduring bedrock. A symbol now lives in the collective imagination, a set of lines on stone. Long past the quiet debates of academic journals, the image of these parallel grooves has stepped into a brighter, wider light. You can find them featured in popular science documentaries, their stark forms narrated by voices filled with awe. They appear as plot devices in novels of speculative history, where they are gateways to lost worlds or evidence of forgotten civilizations. Online, entire forums and social media groups are dedicated to dissecting their mystery, with amateur sleuths and professional researchers sharing satellite coordinates and debating theories across digital campfires. This widespread fascination is about more than just geology. The grooves have become a powerful cultural icon, a visual shorthand for the idea that our planet still holds profound secrets. In a modern age, where satellite imagery maps every square mile and search engines promise instant answers, these enduring, unexplained lines are a potent reminder. They tell us that some mysteries are too large, too deeply etched, to be solved with a quick query. They stand as monuments to the unknown right here beneath our feet. They represent the thrilling possibility that the grandest narratives of Earth's past are not yet fully written, that our understanding remains a work in progress. This transformation from geological feature to cultural symbol speaks to a deep human need. We are drawn to puzzles, especially those written on a planetary scale. The grooves satisfy that craving perfectly. They are tangible, visible to anyone with a satellite map, yet their meaning remains just out of reach. They are the perfect mystery, concrete in form but infinite in possible explanation. In this way, they have come to symbolize curiosity itself. They remind us that the drive to ask why, to look at a simple line and see a story, is what propels discovery forward. They are no longer just scratches on rock. They have become an emblem for the enduring human quest to understand our place in a world that is still wonderfully, magnificently unknown. But with growing attention comes a profound responsibility. These parallel grooves are more than a puzzle, they are a fragile, renewable archive. Each site is a unique page in a planetary manuscript that cannot be reprinted. Once a section of grooved bedrock is chiseled away by a collector, by graffiti, or paved over for development, that specific piece of evidence is gone forever. The information it held, perhaps the crucial clue that tied a site in Arizona to one in Africa, is erased. This transforms the mystery from a purely intellectual challenge into an ethical one. How do we investigate without destroying the very thing we seek to understand? Responsible research today relies on a principle of minimal impact. Scientists increasingly use tools that gather data without removing the stone. High-resolution three-dimensional laser scanners can create perfect digital replicas of a groove, capturing every nuance of its depth and texture. Advanced spectral imagers can analyze the rock's chemistry from a distance. When a physical sample is absolutely necessary, it is taken with the precision of a surgeon, a tiny core no wider than a pencil, leaving the vast majority of the feature undisturbed for others to study. This careful approach extends beyond the rock itself to the landscape and communities that surround it. True stewardship means collaborating with local authorities, and most importantly, with indigenous communities for whom these lands are often ancestral home. Their traditional knowledge can provide invaluable context about the site's history and significance, forming a partnership where science and cultural heritage work hand in hand. Furthermore, the ethos of modern exploration demands transparency. Findings, data, and even three-dimensional models are increasingly shared in open-access databases. This builds a collective knowledge base, allowing researchers from every corner of the globe to analyze the same evidence, test their theories, and contribute to a unified understanding. It prevents the tragedy of a vital measurement being locked away in a private notebook, lost to the broader quest for answers. Ultimately, these grooves do not belong to any single researcher, nation, or generation. They are part of the common heritage of humanity and of Earth's own natural history. Our approach must be one of humble stewardship. We are temporary custodians of a message that has endured for. Our task is to listen to that message, to learn from it, and above all, to ensure these enigmatic lines in the stone remain intact, clear, and waiting. For the curious minds of the future who will bring new questions and new tools to this ancient mystery, The power of these silent lines is rooted in something deeper than science. We are captivated because the grooves speak directly to the architecture of the human mind. We are innate pattern seekers, wired from birth to find order in chaos, to see faces in clouds and constellations in stars. The precise, unwavering parallelism of these markings triggers that instinct with overwhelming force. They do not look random or accidental. They look deliberate, purposeful, almost designed. Our brains immediately whisper the word intention, even as our rational selves search for a natural cause. This tension is magnetic. It pulls us into the mystery, making us wonder if we are looking at the work of an unknown intelligence or a force of nature so coherent it mimics one. This enigma perfectly intersects several of our most profound fascinations. It brushes against the allure of ancient, forgotten civilizations, the tantalizing possibility that a sophisticated culture we have yet to discover might have left a mark upon the world. It touches our curiosity about lost knowledge, secrets the Earth itself has kept. Most powerfully, it delivers planetary drama on an epic scale, a story where continents are the canvas and unimaginable forces are the brush. Standing before these grooves, we are not just observing a geological feature, we are feeling the immense weight of geological time. We sense the fleeting nature of our own existence against a backdrop where mountains rise and fall, and oceans can race across deserts. It is a humbling, awe-inspiring sensation that connects us to the raw, untamed power of the planet, a force entirely beyond human control. In our current age, we are saturated with information, yet often starved for genuine wonder. We have answers at our fingertips, but few mysteries that truly endure. This is why the physical, tangible nature of the grooves is so vital. You can see them on a satellite map. You could, in theory, travel to a remote desert and run your fingers along their smooth, ancient channels. They are not a theoretical concept or a digital abstraction. They are a real, physical puzzle etched into the very foundation of our world. This provides a grounding counterpoint to the noise of modern life. It offers a direct, unmediated connection to a story that is both profoundly old and urgently unresolved. The mystery does not live in a library. It lives in the stone beneath the open sky, inviting anyone who looks to become part of the search. To feel that spark of curiosity that reminds us our world is still a place of deep and magnificent secrets waiting to be understood. These parallel lines in stone remain one of our planet's most captivating open cases. We have walked the solid ground of the glacial theory, felt the cataclysmic force of the tsunami hypothesis, and peered into the speculative frontier of electrical scouring. The evidence we have does not form a single, perfect picture, but rather a brilliant mosaic, each piece reflecting a different facet of a profound truth. What emerges clearly from this scattered light is a global signature of immense power. These grooves are a whisper from a time when Earth may have endured forces of almost unimaginable scale, events that reshaped continents in a geological instant. They stand as a permanent challenge to our understanding, urging us to keep questioning, to keep exploring, and to bravely synthesize knowledge from across the scientific spectrum. This enduring mystery is not a sign of science's failure, but of its greatest strength and deepest inspiration. It is a living reminder that our familiar world, mapped and measured, still holds profound secrets written in its very bones. The story is not over. New tools and curious minds are adding to the map every day. We would love to hear your perspective on this journey. Which theory resonates most with you and why? Share your thoughts in the comments below. If you are captivated by the Earth's hidden stories, subscribe to join us as we continue to unravel its greatest enigmas, one layer of stone at a time.